Today we are going to look at some of the cockpit instruments of the SR-71 and discuss the features of each to help us understand the SR-71's cockpit much more. As simulations become more complicated, the instruments will display nuances alongside the information we expect. But if we aren't used to looking at analog instruments, this will help us by thinking of the layout. I've spent a lot of time reading through flight manuals, listening to the SR-71 pilots as well as reading their books. I've also spent a lot of hours with the Blackbird Simulations SR-71 since release, and it's truly fascinating. With that in mind, welcome to the cockpit of the Blackbird Simulations SR-71A for MSFS 24. This is a 1960s era cockpit and is all about the gauges and switches. Instruments are grouped together in sections, and as you fly you read them by scanning, like in an old Comanche light aircraft. Right in front is a rather large instrument which is the attitude direction indicator, the ADI. It includes an artificial horizon where white is the sky and black is the ground. In the middle is a W representing the aircraft wings and a dot for the nose. The dial allows you to adjust the pitch position of the nose but doesn't command an action. The ADI was modified in the SR-71 to be more pitch sensitive, especially useful when flying at night. The white bars around the bottom are the bank angle markers, and there's a white arrow pointing down showing what the current bank angle is. For reference, the white diamond is the 45-degree marker. In the cruise, bank angle is reduced to 32 to 35 degrees while supersonic. Below the angle markers there are 3 white bars and a small white ball. The white ball displays the aircraft's turn and slip indications. To correct, you simply apply small amounts of rudder in the direction of the ball when in a turn. The climb and descent gradients are measured in degrees, where a line is plus 10 degrees and a dot is plus 5 degrees. The first 2 lines, up, are 10 and 20 degree markers, and the 2 first dots are 5 and 15 degrees. The yellow horizontal and vertical bars are the flight direct with ILS glide slope. The horizontal bar displays where your pitch should be in flight, and the vertical where your roll should be. This information is either from the ANS or INS systems, selected using the @ref select switch. The airspeed indicator works in tens and hundreds of knots. The speed is represented as indicated airspeed and has a maximum reading of 600 knots. The Mach meter on this instrument doesn't work. At supersonic speeds, this instrument becomes unreliable due to heat, pressure and shock waves. The altimeter works as it would in a Cessna. The long bar for hundreds of feet, the short bar for thousands, but also has an outer marker triangle for 10,000s. The altimeter also has a pressure set dial with the current pressure in inches of mercury displayed in a small window. The instrument should display a white and black warning stripe when below 16,000 feet. The inertial lead vertical speed indicator, IVSI, shows the rate of descent in feet per minute, FPM. Found on light aircraft, it operates the same way and shows up to 6,000 feet per minute in either direction with no lag while supersonic. However, the IVSI also has a built-in mechanism that is sensitive to 0.7 to 1.4 G load factors, which changes the static pressure. This change causes a change in the rate of climb and descent indications when the Gs are increasing or decreasing. Usually this happens during altitude changes where the instrument will continue to display, causing a lag effect. At high altitudes above 40,000 feet, the IVSI could be showing only 1/3 of actual conditions. The horizontal situation indicator works like on light aircraft. Within the compass rose is a course indicator that has a moving centre part to indicate where your course is in relation to the aircraft. Around the outside of the rose is a triangle that rotates around until there's a TACAN or ILS localise the signal. Then the arrow points in the source's direction. The grey square is your selected heading when in heading hold mode, or for reference in TACAN or ILS modes chosen using the display mode selector switch. The left dial changes the required heading, and the right dial changes the required course heading. The readout on the top left is the distance measuring equipment DME display for range from the source radio tuned in nautical miles. The right readout is the current course heading. The angle of attack AOA gauge displays the current angle between the aircraft and the direction of flight in 1 degree markers, between -5 and +22 degrees. It has a red marker, no-go indication of 15 degrees nose up. This instrument responds to signals from the computers. No computers, no AOA. An accurate reading can only be ascertained at or above 100 knots equivalent airspeed. When level, the angle of attack reading will be 1.2 degrees greater than the wing due to the wing's negative angle of incidence. The compressor inlet temperature CIT gauge measures from the front of the engine and is a crucial instrument when flying supersonic. It has a left and right needle and a red marker at 430 degrees centigrade. However, the max temperature the aircraft can fly safely below is 427 degrees centigrade. This temperature is the danger do not cross limit for the engines. The compressor inlet pressure CIP indicator measures from the front of the engine and displays indicated static pressure in PSI. It has left and right needles for each engine and a striped third needle displaying normal expected pressure. The pressure will change with keys and Mach. If the striped needle is substantially different to the left and right needles, this would mean improper inlet operation. Higher actual pressure can produce unstarts at normal speeds and altitudes. Lower actual pressure shows improper spike or bypass door settings. The triple display indicator TDI displays 3 flight critical measures: knots equivalent airspeed, altitude in feet, and Mach number. This is used for transonic climb, descent, and supersonic cruise. It also features a scale for maximum knots at different altitudes in the climb and descent. There are 5 indicators for each JT11D-20 J58 engine located together in a vertical stack. The engines produce 25,000 pounds of thrust in military power, max dry power without reheat, and 34,000 pounds in afterburner. The tachometer measures the rotational speed, RPM, in the main gearbox. The small dial measures in hundreds and the large dial measures in thousands of revolutions per minute, or RPM. The engines will idle around 3,500 RPM and will reach 7,100 RPM in military and afterburner settings. However, at supersonic speeds, the engines are designed for continuous operation when compressor inlet temperatures, CIT, reach 400 degrees Celsius and above. The bleed air function operates at a CIT of 85 degrees Celsius to 115 degrees Celsius, which is Mach 1.8 to 2.0, creating the ramjet effect. On the ground and at low Mach numbers, the engine speed will vary, but at higher Mach numbers, engine speed remains constant for all throttle positions including idle. Therefore, in the afterburner range and at high Mach, the system will adjust the exhaust nozzle to maintain constant RPMs. This means that throttle changes in the afterburner settings and at high Mach will only change the fuel flow, nozzle position and thrust. At a fixed throttle position, engine speed will only vary based on the main fuel control schedule when CIT and Mach changes. This is why it takes a while during deceleration and descent for the RPMs to again vary with throttle changes. It isn't stuck and may jump depending on the throttle position. The exhaust gas temperature, EGT, is measured near the afterburner spray bar rings after the bleed bypass tubes. It is connected to the D-rich system should the EGT climb higher than 860 degrees centigrade. Each gauge has a digital display which shows EGT in degrees Celsius. There is a red hot warning and a cold yellow warning on the instrument. There is also a red warning light that illuminates if the EGT reaches 860 degrees Celsius. The gauge also has a red off light. The exhaust nozzle position indicator, ENP, measures the nozzle position in the aft section of the engine. This indicates an index from 0 to 10, where 0 is closed and 10 is open. The fuel flow indicator measures the rate of fuel entering the engine from the fuel system. It measures in thousands of pounds of fuel per hour. The oil pressure gauge takes its measurement from the main gearbox and indicates the output pressure from the engine oil pumps. It measures the pressure in pounds per square inch (psi) and ranges from 0 to 100 psi. Note the green normal bands, which fall between 36 and 45 psi. The large fuel gauge shows how much fuel you have either in each tank or as a total on board the SR-71. There is a dial to select the tank or total fuel. The gauge indicates in thousands of pounds up to 85,000 pounds. There are two liquid nitrogen gauges displaying the quantity left in each Dewar flask, located in the nose gear well in litres. Each tank holds 106 litres. Liquid nitrogen is used to inert the fuel tanks, or replacing the oxygen in the unit space. This avoids autogenous ignition in the fuel tanks as they empty during high temperatures at supersonic speeds. The inerting system will also flow whenever fuel tank pressure differential drops below 1.5 psi to maintain the tank pressure 1.5 psi above ambient pressure. The centre of gravity indicator is another crucial gauge in the Blackbird. At takeoff, the CG normally reads around 22%, but in the cruise this should be 25%. An aft CG is the most efficient during the cruise. Note the red band after 25% CG. This is the dangerous no-go area. The CG warning will display after 25% aft and at 70% forward. The fuel tank pressure displays the differential pressure delta P in the fuel tanks during flight. It measures in psi. The nominal fuel tank differential pressure is between 1.5 and 3.25 psi to provide a positive fuel flow to the engines. There is a pressure release valve to stop the differential pressure exceeding 4.15 psi. If this actuates, you can see it venting from the tail cone. There is a row of illuminated buttons showing which fuel tank pumps are actuated. From top to bottom, there is the crossfeed valve, tanks 1 to 6, and pump release button, plus a test button. As tanks deplete, the system will automatically switch tank pumps off and on in a sequence during flight. 1, 3, 4, and 6 is the normal configuration at takeoff, but 4 is released after takeoff. To manage the centre of gravity, CG, there are two fuel transfer switches, a forward transfer and a manual aft transfer. These are used in flight to move the CG around, often to a schedule in the checklist, for the nominal settings. Don't forget to turn these off once the required CG is achieved. The spike position indicator shows the current inlet spike position in inches. The dial shows 0 fully forward to 26 inches fully aft. The computer's DAFIC system will modulate the spikes to capture the shock wave and bring it toward the inlet so it can be used at high Mach for thrust. There are two manual control knobs. should they be needed, beneath the instrument to control the spikes manually, one for the left engine and one for the right. Their default position is in auto. The forward bypass door indicator features a left and right needle for each engine. The gauge shows the position of the doors during flight and descent where 0 is closed and 100 is open. There are also 2 control knobs beneath the instrument for manual control of the forward bypass doors should this be needed. The default position is in auto. There are 3 trim indicators for pitch, roll and yaw. These measure in degrees and are in the default start positions. As you adjust trim for control surfaces, these show by how much in degrees. Yaw indicator shows a left and right needle as there are 2 rudders on the SR-71A. Once used to the cockpit and instrumentation, the SR-71A is designed to deliver the right information at the right time in managing the flight envelope and controlling the aircraft. In supersonic flight, there are some mission critical indications that you must keep aware of and ensure you take the actions needed to maintain a safe flight. In the next episode, we'll be looking at the start and taxi procedures and getting the SR-71 ready for launch.